Hello, Sarah. Hello, Payman. How was your day?
Good.
I think very busy. So, which meeting do you have? Which meeting conflicts with this one?
Actually, I have an appointment, not a meeting.
Oh, okay.
For student health center, so I have to.
So
I'm confused.
education, it's something personal. Okay.
Yeah.
That's so you speak number 2 because speaker number 1 matches well to start with.
I see. It's okay.
Payman, I did look through your slides, and it seems that did you get right figures that you wanted, or something didn't work?
Hello, Dr. Killen. Actually, I add 3 slides to my previous PowerPoint. Actually, I got those results.
Okay, let's before everyone starts, let's quickly look on them because something I was kind of missing. Share. So we want figures like this, right?
Yes.
And you are showing this figure.
Yes.
But on the top of it, there is a. I just do not see the. And then you show 3-dimensional distribution of the electrostatic potential map. So the main idea is that it's like we invite kids from kindergarten with paintbrush, and they paint on the top of this image. So this purple surface should be not purple, but green and yellow, depending on different spots.
I got you.
So you can probably right now there's not enough time. Maybe if you share your slides, you can fix it now, or if it's not possible, you just mention that with one additional step, it will become colorful. And practically, one just clicks on a surface and adds, like I think you're showing it. So after the total density is available, you're clicking this new surface once again, and then select ESP. And then this the ESP map is arranged on a top of this thing that you show purple. Make sense?
Yeah, actually, let me to try it again.
Okay. Yeah, and then maybe because you're not speaking the first, you have like a couple of speakers in front of you. Maybe you can fix it.
Right.
Okay. Yeah. Thank you. I'll stop sharing. And there are more. Admit. Oh. Hello, Adam. Hello, Hadassah. Nice seeing you connected. So I think we should start. Let me make everyone a co-host just in case. And if you are not speaking right now, and as a co-host you see that anyone wants to join, feel free to admit if I do not react immediately. Hello, Lola. Nice seeing you connected.
Thank you, Dr. Killen.
Thank you for joining in the day when you are not presenting. It's appreciated.
Okay.
supporting the event. Okay, so we are in the computational chemistry CHEM 676, and for one of us it is 476. So the first speaker is Adam, second speaker will be Sarah, and then we'll go in the ascending order of numbers. So please try to stay within 5 minutes. Questions are very welcome. And first speaker, Adam, please start sharing screen and presenting. While speaking, try to enable camera because it helps to recognize what is being said. Adam, would you like to share your screen? Testing connection, testing connection. Okay, I think, Adam, if you cannot connect right now, let's swap your order with Sarah because, and then we'll try to give you an opportunity to speak after. So Sarah, please start. The order of presentations is a little bit changed, but original order was planned to make it in a logical consequence, but we may browse through recordings and watch it in the right order. Okay, Sarah, please start sharing your screen and making your presentation.
Hello, everyone. So today we're gonna see how can we rate and run Gaussian simulation on CCAST prime. So first of all, you need to sign this agreement. So when you run the simulation, it will give you access to Gaussian on CCAST. You can find this through this link in the presentation, or you can contact CCAST support to give you this agreement to sign up, and then you can proceed with running Gaussian. So just a note, we will not run it as a way on photon cluster, just running Gaussian to submit the jobs. So Gaussian and CCAST will be only used to visualize or prepare input files, just preparing it. And the jobs must be submitted in a queuing system. We're gonna see how now. So first of all, you have to prepare your input file, which is used to be .com file, as you experience with photon cluster, but here it should be in .inb extension. And it also need to be with another input file that is the script, the BPS script, that one that queuing the jobs in CCAST system. So let's go see how the input file, the .inb file, is almost the same like the one we get from .com, but you need to be careful with the format of your file. So here you need to define your memory and be careful to be a little bit less than, I'm sorry about that, to be a little bit than the memory you set in the batch file or the submission file. And also the number of shared process should be the same as the number of CPUs in your submission file. You had to not have, but it's recommended to add this lambda co-workers, workers, because the batch file already has the lines of Linda workers for parallel computational work. So just keep this comment and keep it blank, because the job submission file will automatically fill the vacancy here. And then here you should set the name of your check file. And the following is a blank line. Be careful to keep this blank lines as blank lines. And also this is the computational settings, the title, the spin, and charge, and atomic coordinates. All the rest are exactly like the .com file you get from Photon cluster. Then you need to prepare your VBS file or submission file. So you need to care about only these 4 points here. So here you need to set the name of your submission job. So when you look at your jobs on CCAS, you can recognize which one is running and which one is not, which one is done. So just for your preference, here you need to select the memory and number. Of course, make sure the memory here should be higher or at least equal the one you have in your input file, and the number of CPU should be exactly as the one in your Gaussian input file. Here you set the time that is allowed on CCAS for your job. So if you expect your job will take like 10 hours or 11 or 12, just put it 20, because if it took more than that time, the CCAS will terminate your job even though it's not done. So add the time to be a little bit more than the expected time for your job. And also don't add it as too much higher than the expected time, because that will give you that will put you in a queue for a long time. So now you're done with the main settings. Now look at your input file. Here you need to write down the name exactly as the name of your input file, because it's different a little bit. It won't run. And also set the name of your log file that will be generated once you submit a job. So this is basically the 2 input files you need to run or submit a job. And I'm sure all of you know how to submit this job. Just command Q sub and then write the name of your .bbs file. Okay, now how to use Gaussian view. So just go to apps. So this is the homepage of On Demand, CCAS On Demand. Go to apps, and then from there go to all apps. You should find Gaussian view apps there, but if you don't, please contact CCAS support. They will check that for you. And okay, so now I went to apps and then all apps, and then I clicked on Gaussian view. I will get this page here. I will select the number of hours and of course the project I am in. And if you need to set your email, I never added my email actually. And then you click launch here. It will give you a few seconds until it starts running like this. So all you need is to select the quality if you need to generate image, or just decrease it if you don't generate image, just to save your time, and then launch it. But the problem is it's not very handy that much if you're running very large molecules, because it has only 4 cores, but it's good for steady work, like normal work. So so this is the Gaussian view on CCAS. It's not flexible as the one you find on Photon, but it works. It's not handy to build structures, because not all the time the graphic will work perfectly, and some delays sometimes. So I would recommend you to build your structure and then import them, and then work on it, either to generate initial input file, the .com file you will generate from here. Make sure you sit in this format, you add this command lines, you make sure of your blank lines and so on. And yeah, that's it. That's all you need to do for CCAS on Gaussian. So thank you for your listening. Any questions?
Okay, please join me in thanking Sarah. Paper is open for discussion. Any questions are welcome. I have a very basic question just to start from. How do I know that the job, Gaussian job that has been submitted with Q sub command has been completed? Is there a way to monitor the progress, especially if it is long job?
Yeah, I have this. So CCAS has a few comments. You can look forward your submitted job. Q state, then minus U. Of course, this is small. And then minus U, and then my username, which is Sarah.Tulba Salim, and then that's it. It will give you all the states, all the jobs you submitted, either in queue or running. But if it's done, I don't see there. There is another command to see all jobs that is submitted, done, terminated, whatever. But I don't remember it for now. But this one give you the queued and the running one. So if it's not in the running one, I go to my log file and I look at the end of the log file. Just I write, for example, tail, and then obt.log, and then I see at the end there's a termination, normal termination of my job, and then I know it's working fine. Yeah.
Thank you.
Yeah.
Thank you, Sarah. Are there more questions to Sarah? Questions 1, questions 2, question 3. Please join me in thanking Sarah.
Yeah.
And let me check. Adam, do you have your camera and microphone?
Yeah, I had to grab a webcam and a microphone from somewhere because my laptop was broken. Okay. Let me share my screen. All right. You guys hear me?
Yes, you can see your slides, yourself, and we can hear your voice. Please go ahead.
Perfect. All right, I'm just going to be talking about the available methods, or some available methods that we have in Gauss view, particularly to predict electronic structure. So these are going to be mainly these kind of 4 or 5 methods. The first is Hartree-Fock. That's pretty self-explanatory. We know what that is. That'll give us energies. DFT can also be a very powerful tool to us. We can do even time-dependent DFT using Gauss view. I'll talk more about that later, though. Mulder-Plesset perturbation methods, that's MP2 and MP4. I'll talk a little bit about those too, and then CCSD, which can give us a good idea of some excitation energies for smaller systems. And also, we'd like to go over some basis sets and essentially, I don't know, just explore that. Okay, so the Hartree-Fock method makes a few assumptions. We assume the Born-Oppenheimer approximation. So that means that wave functions in nuclei and electrons can be treated separately. So nuclei and electrons, yeah, we just treat them separately. There's no relativistic effects that we factor into the calculations. The variational solution is a linear combination of a finite number of basis functions. They're usually orthogonal, though. And each eigenfunction corresponds to one single Slater determinant. Also, the mean field approximation is inherently implied with the Hartree-Fock method. So those are the basic assumptions. If you kind of get looser on the last two, each eigenfunction corresponds to one Slater determinant and the mean field approximation, then you will have most post-Hartree-Fock methods. And so that's where they kind of differentiate. So density functional theory is also another tool that we can use. It's very widely used. It's used to describe many body systems like Hartree-Fock can be. It relies on functionals instead to describe electronic structures. So some examples of this are B3LYP. It's a 3-parameter hybrid functional. This was actually considered to be one of the first improvements over Hartree-Fock for DFT at the time that it came out. And then PBE, as Gaussian listed, it's just PBE. It's just an exchange correlation functional. And there are many, many more, as you can kind of see here. They're all used for different things. They all have their own niche. So the Moeller-Blessed methods, this is MP2 and MP4. Moeller-Blessed, it's useful for approximating correlation energy. The 2 and the 4 mean second order and fourth order. So it's the order to which it is computed. MP2 is simplest, as the number would suggest, and MP4 is slightly more demanding. Some people say that MP4 is not much better than MP2 for calculating energies, even in smaller molecules, but it does have some uses, as in thermochemistry and stuff like that. You can get an additional option with MP4 to include or exclude triple substitutions. So CCSD. It's also used for describing many-body systems. It'll give you 1 and 2 electron excitation energies. So this is kind of really important for like doing photo excitation in smaller systems. This is usually like a 2 to 4 electron system. These are they use the Hartree-Fock orbital approximation method, but they specifically kind of describe excitation energies. So these account for the electron correlation by using a multi-electron wave function. And before I want to get on to basis sets, I should mention that for Hartree-Fock and density functional theory, kind of gonna bring you out of here for a second. You can go to the method here, and you can select TD-SCF. So you can either do, so that means that you can do time-dependent DFT, or you can also do, I guess, time-dependent Hartree-Fock or CCSD, or you can pick a semi-empirical method if you want to be quick. Yeah, those are really, really useful for describing how, of course, systems interact across time. Okay, let's talk about some basis sets. So you have your big list of basis sets here that you usually you'll see in your Gauss view. So you have your X, Y, Z, G. So that's 321G, 631G, et cetera, et cetera. So X is the number of Gaussians describing the core atomic basis function, while Y and Z describe the valence orbitals. So these are used in the calculation, and basically they are all of different size. They use different methodologies and different parameters. The CCPV, DT or Q, Z, DT or Q mean double, triple, or quadruple. Correlation consistent polarized valence zeta. These are right here, I guess I have in blue, and then the Los Alamos National Laboratory. So these are LAN L2DZ and LAN L2MB. Double zeta and minimal basis. These also include parameterization for heavier elements, but you should probably only use it for that, because it's not much better than, say, 321G for probably like CHNO in a really small system. All right, so questions?
Please join me in thanking Adam. It was breathtaking talk. I even forgotten to unmute the microphone. Any questions?
Yes, I have a question.
Yes, please, Rizvi.
Well, you were saying about time-dependent method. So I want to ask, what is the advantage of that time-dependent method, or how it is different to the technique we done in the lab?
The time-dependent method. Okay. Let's take CCSD for an example. The energy it may change over time, right? So if you have a photo excitation, the energy at let's say x1 might be different from the energy at x 100 or x 96 or something like that. Time steps, I guess. So it's you can look at the energy between those time steps. So it gives you I guess more data for that.
Okay. All right. Thank you.
Yeah, thank you, Rizvi, for the question. Thank you, Adam, for the answer. Let me add to this discussion. So you both were very brave to touch this area. We plan, if things go favorably, we plan to dedicate the whole month of April to focus on this. And the time dependence in the name of the method doesn't mean actual time dependence of the calculation. It's impossible to discuss in a very short time, but briefly, if the external perturbation like light is promoting your molecule from ground to excited state, this is a very time dependent process because electromagnetic field is oscillating like crazy, right? And the philosophy and original equations where people start to derive how to treat excited states include time dependence of electromagnetic field over time, which is like it changes phase like each femtosecond or so. But then for practical comfort, one performs not in the computer, just in a head, in derivation of equations, performs Fourier transform, where all fast oscillations are just taken as a component of certain frequency. And then equations for these processes of excitation are treated in the frequency domain, which originates from Fourier transform of the time domain. But because original equation started from time dependence, it inherits this very deceptive name. So yeah, enough. But I really appreciate you included this into presentation and into discussion. It's important and it gives heads up for the whole month of April. Any more questions to Adam? Questions 1, questions 2, questions 3. Please join me in thanking Adam. So you can stop sharing. So next presenter is Amara, and let me congratulate all ladies in this class with International Women's Day, which in some countries is celebrated, in some not. But okay, Amara, floor is yours. Please start sharing.
Thank you. Hello everyone. I will continue with the previous presentation, and I will talk about the available tasks that we can perform by using the Gauss view. So there are 6 most common type of calculations that we can do by using the Gaussian. That is energy optimization. We can calculate the single point energy. We can calculate the frequency from the vibration of the from the symmetry or vibration of the bonds of the molecule. We can also select the stability of the wave function. We can calculate the molecular orbital and population analysis, and we can use the IR, UV visible, and NMR calculation of the molecules. So first is the geometry optimization. Geometry optimization is to find out the minimum energy, and the software use the wave function and energy of the starting geometry, and it use algorithm to search for some new geometry. And what information we can get from the geometry optimization, we can get the atomic coordinates of optimized molecule. We can get the different optimized parameters that we set in the input file. We can also get the information about the homolume eigenvalues, and we can get the atomic charges and dipole moments. So here is the window. We can see in the job type, when we select the optimization, then we can set the values and we can start the calculation. So we can also calculate the single point energy, and that is like the point energy of the fixed geometry. We can usually done this calculation at the start when we build a molecule. So we need to find out about the nature of the wave function of this molecule. So there are the methods that we can choose for this calculation, and Adam has already explained these methods. So here is the output file. When we load this output file and we go to the results and summary, then we can select the IRC path. Then we can directly show this plot. We do like we can directly view the energy during the triangle calculation. So just like this, I have run this molecule, and when I get the output file, I open it through this IRC path, and it gives me the total energy, and it also gives me the RMS gradient of the molecule. So UV visible spectra, I can also calculate the UV visible spectra from the Gaussian, and I need to also, when I go to the result, but for the UV visible, we need to select the DFT method instead of Horty-Fock method. So when we select the DFT, and then we can also get the UV visible spectra of the molecule. First, I use the benzene, and I will get the straight line for the UV visible, but then I change the molecule, and so here I got some UV visible. So I think it might be depend on the energy difference between the electronic states, and when this energy difference coincide with the initial incident wavelength, so then we will get the UV visible spectra. So it depends on the symmetry. Some molecule have will show the straight line, but some molecules give us the peak. And we can also find out the IR spectra from the frequency and vibrations of the molecule. And here you need to, in the job time, you need to specify the optimization plus frequency to get the IR spectra. And these are the output files that you can select according to your, that you want in your output calculation. And then you can run the simulation. After that, you can go to the result and summary and IRC path. Then here you will find out the IR spectra of the molecule. And it will also give about the other information from where you can start. If you start the animation, you can find the video of the molecule that is moving during the calculation, how it moves during the calculation to get the IR spectra. Thank you. That's all from my side. If you have any question, please welcome.
Okay, please join me in thanking Amara, and presentation is open for discussion. So are there any questions? It seems like everyone is happy or everyone is shocked by a lot of information. So why you've mentioned that UV spectra didn't work with Horty-Fock when needs to select DFT. Can you please expand on this? Like why, or like just add more about this subject?
I think UV visible depend on the energy difference between the ground state and the excited state. So in DFT calculation, it gives us the information about the difference between the energy difference between the orbitals?
I never saw this prescription. I thought one can do spectra with Hartree-Fock as well, but they will be just not precise. For spectra, as Adam mentioned, one needs to do not simple DFT or Hartree-Fock, but add this TD. So TD Hartree-Fock or TD DFT should give the spectra.
Yes, it should time-dependent DFT.
Okay, yeah, then it makes sense. More questions to Amara? More questions, one. So the options that Amara did show could be very valuable to those of us who will decide to do the mini research project at the end of semester with Gaussian, which everyone is very welcome to do. There will be, I will be inviting everyone to use other software that we start tomorrow, but Gaussian is great. If you can do your project with Gaussian, it will be really great. So more questions, one, more questions, two, more questions, three. Let's thank Amar once again. It's really useful. So now we are coming to a stage where several subsequent talks will show how to visualize Gaussian output, Gaussian results. And I believe the next presenter is Payman. Payman, would you like to share your screen?
Sure, definitely. So
Okay.
please let me share the PowerPoint. So can you see it?
Yes. If your equipment has camera, please consider to enable it.
Of course.
Okay, thank you.
So,
Please.
hello, everyone. Today, I'm going to talk about ESP potential, which is electrostatic potential, and molecular charge visualization in Gauss view. So let's talk about isosurface. Let's talk about some definitions. So what is an isosurface? Isosurface is a surface that includes all points representing a constant value. And that value could be many things, depending on the nature of our problem. That value could be a temperature, which is shown in the first picture, velocity, which is shown in the second picture based on the CFD simulation, or electron density, that you can see it in the third picture. An isosurface basically is a level set of a continuous function in three-dimensional space. So, as I said, one of the types of isosurfaces is electron density. What is electron density? In computational chemistry, electron density is a probability of presence of electron in a specific region at an infinitesimal element of a space surrounding any given point. Based on this definition, because the electron density is a probability, it means that this value is a scalar quantity. In simple systems such as one electron system, the electron density is equal to the square magnitude of the wave function. In Gauss view, after calculation is done, you can go to the results tab and choose the surface contours. Then you need to select new cube. After that, in the pop-up window, you need to choose the total density. Then click OK. After a while, you need to choose, after it's calculated, you need to choose the new surface from the surface available tab. And you can see the surface, electron density surface in your model. But it's you cannot see the contours. For seeing the contours, you need to select the surface action. From the surface action tab, you need to choose the new map surface. After then, just choose the ESP in the types and then click OK. And after a while, it calculates the contours of the model that you can see in this picture. So this counter shows the electron density in the chosen molecule. The next step is to see and actually try to visualize the electrostatic potentials in our model. So basically, the electrostatic potential is the proton potential energy at a particular location of a specific region of a molecule. Positive potential corresponds to repulsion, and the negative potential corresponds to attraction of a proton by electron density in a molecule. So in Gauss view, for seeing the electrostatic potential ESP, you need to go to the results tab, choose charge distribution. After that, you need to go to the counters available section, choose the new counter. And in type, in a pop-up window, you need to choose the ESP as type of the visualization. And then you can see these counters of electrostatic potential, which is shown in the orange lines in your model, in the molecule that you calculated before. Another visualization is molecule population analysis. Molecule population analysis is an estimation of partial atomic charge in any molecule. Partial charges are the results of asymmetric distribution of electrons in bonds. And in molecular mechanics, force field, partial charges are used for computing electrostatic interaction energy. In Gauss view, for seeing the charge distribution, you need to go to the results tab, choose the charge distribution, and in a pop-up window, you choose the molecule in the type. And in the second row, you can choose the range of the color for better color range for better visualization. And as you see in this picture, you can see the partial charge for each atom. For example, here in oxygen atoms, the charge is very close to 1. It means that it's actually close to -1, which is about 0.982, and it means that this atom has attracted electron, almost 1 electron. Or this, for example, this central atom, the charge is about 2.22, which means it's almost has lost 2 electrons. Thank you for your attention, and please let me know if you have any questions.
Okay, please join me in thanking Payman. It's a great presentation. So talk is open for discussion. Any questions? Please bring your slides back. There will be some questions based on content of the slides. Okay, let's flip a few slides back. More. Yeah, this one. No. This one is contours. So let's memorize these contours. And now a few slides back. More. And this one. So what is there any similarity? Is there any connection between this map and the contours? And just tell what you see. And also, I wonder if it is labeled correctly, if it is electron density, or it would be more correct to call it electrostatic potential map.
That's a good question, actually. I'm not sure, but I can explain it in this way. I think the counters shows the fixed value in a space. but this density shows the variation of values.
So you see that the colors are different, right? There are
Right.
green areas, and close to the metals there is a blue area, right?
Right, correct.
So let's go forward to your contours. And there are not too many, but if you would generate a little bit more of those, there are contours around the metal, and there are contours that embraces the whole molecule, but there could be additional contours that kind of repeat the shape of this all water groups.
Yes, correct.
Okay, so I'll better say it. I was intending to ask a question, but it could be too much. Or you can try question number 2, which will be connected to question number 1. In the Hartree-Fock theory, there is a potential, self-consistent potential that includes all electrons affecting the last electron, right? So what is the connection with this potential and your electrostatic potential map? Would it be possible to say they are the same? The electrostatic potential map is just combined action of all electrons and ions that will affect any charged particle approaching to your molecule.
If the ESP is the contribution of all electrons, that's your question?
Huh?
Based on the theory, because we only consider the last electrons, I think, no, we cannot say it's the contribution of all electrons.
Wait,
I'm not sure.
The last electron for which we find molecular orbitals, right?
Yes, correct.
It is being affected by repulsion of all other electrons.
Right, right.
And this combined activity of all other electrons and all ions is called potential, which is included in the Fock operator. Okay?
Correct.
And the electrostatic potential map is basically the same thing. You just visualize the potential in the Fock operator. So the map that you are showing right now with contours is showing several contours in this three-dimensional space. And I like it, and you like it. I think it is most natural. But for in chemistry community, there is a different way to represent it. So one selects one of these contours, right? One of the contours which is made based on the density, not potential, but density. So along one makes contour along which the density is the same. And then one travels along each point of this contour and makes it either blue or red, depending on the electrostatic map, electrostatic potential. So let's go back to your colorful thing. Okay, so the shape of these bubbles are isocontours for density. But the color of these bubbles in one or another area represents electrostatic potential. So it combines density and potential. And therefore, same as on geographical map, when colors are changing, this is called electrostatic potential map. Okay, does it make sense on your side?
Yes.
Okay, yeah, thank you for supporting this discussion. I think it is really great that we went over it now, and I think everyone in class benefits it. So are there more questions to Payman? More questions 1, more questions 2, more questions 3. Let's thank Payman once again.
Thank you.
Thank you. Great talk. I like it. So now we do have 3 more presentations, each of which will be on the visualization. So Umar, would you like to share screen?
Yes, just a minute.
And if your
Can you see the
equipment,
slides?
if your equipment has camera, please consider to enable it. It will help to.
Yes, I have already opened my camera.
That's great. So please go ahead.
Oh, okay. So molecular orbitals and then form check, cube gen, and concept of isosurfaces. So when we talk about the molecular orbitals, it is the location and wave-like behavior of an electron in a molecule. And it is helpful in highlighting the probability of finding an electron in any specific region, and you can see some shapes of different orbitals. So to visualize these orbitals, I have taken molecule zirconium hydroxide. Its .com file or its structure was initially built in Gauss view, and then it was optimized with the Hartree-Fock and then the base set of land L2DZ. That is, you can say, some very common basis set for the metals. And when we see its charge, it was 0 and it was singlet because the overall charge was 0 on that molecule. Okay, so after optimization, the log file was generated and we can see some features in the title card, such as the such as the energy, and we can also verify this energy by running that file. And similarly, we can see some other information, some other confirmation of the method we have done with the .com file, the Hartree-Fock and basis set, and then again the neutral and the singlet state of the molecule. To visualize the molecular orbitals, the log file has also given or showed some more details, like the occupied orbitals and the empty orbitals or unoccupied orbitals. So we can count these occupied orbitals, and we can generate the cube files that are helpful in highlighting these molecular orbitals. And before that, we have to convert the check file of that optimized structure into form check. And this form check is basically, we can say, an input for the visualization software. So we simply put a command of form check that make a form check file. And secondly, we put a CubeGen command for converting that form check file into .cube. So we calculated all those occupied orbitals, that was 24 in our case. And after that, we have also built another cube file by adding one unoccupied, or we can say the LUMO orbital, so that we can make a comparison between the HOMO and the LUMO. So when we open the cube file, we can say the HOMO file, it doesn't show anything, but when we click on the results and in the drop-down menu, when we select the surfaces, then new surface, so we can see these figures. And we can modify the surfaces by changing the values from here. By default, it is representing 0.02, but we can modify 0.04, 0.06, 0.08 as per our need, as I have done with different values. And we can see here these orbitals, the occupied orbitals, are mainly localized on the oxygen atoms. Here we can see the d orbitals, because the oxygen has gained electron from this zirconium metal, and that's why it is presenting in the p orbitals, in their d orbitals, I believe, because they were empty. And
P on oxygen.
this is, sorry,
It's P on oxygen, right?
yes, it's p on oxygen. Yes. And then when we change its surface value, ISO value from 0.02 to 0.04, then we can see the differences. And as we increase the value, our cloud or our molecular orbitals are, we can say, shrinking, or they are having lesser size. Similarly, when I generated the cube 25, that is the LUMO, I can see different shapes and different values, 0.02, 0.04, and 0.06. And here we can see the virtual orbital, or we can see the unoccupied. The LUMO one is more localized towards the zirconium or the transition metal. So this was all the concept of generating the molecular orbitals and visualizing it. Thank you.
Okay, please join me in thanking Umar. Any questions are welcome. I have a very basic. Why zirconium instead of titanium? Was it intentional, or it just was a human error? You click on the different button. Or you're doing project for your research. You are interested in zirconium compounds.
Not at all. Actually, I was trying to practice the tasks, the skills we have learned in the lab. So I tried the same molecule, or you can say the molecule that has same features. So I found, I don't know whether I was right or not, but I found the zirconium that is again the transition metal and has almost same features like titanium.
Okay, yeah, makes sense. Yeah, thank you. More questions to Umar?
Can I ask a question?
Yes, Rizvi, please.
Okay, Umar, you were saying we can reduce the. Can you go to the last slide? Yeah, this one. So here you are changing the value of MO. I think you are increasing it. So I have a very basic question. How large value we can take? Is there any standard value, or are we limited to any range for this?
Well, I think it's just because visualization. For example, we can also visualize that molecule. So it's just, you can say, a better visualization. To get a better visualization, we are changing its value. I think it's the simplest answer. I don't think so there is anything standard in that.
All right, thank you.
Thank you for bringing in this discussion. Okay, let's count down. More questions to Umar 1, more questions to Umar 2, more questions to Umar 3. Let's thank you once again. So we have 7 minutes and 2 talks more. I hope we can stay a little longer. Just a few minutes. Next speaker is Hanmant. So please share your screen, enable your camera if possible, and go ahead with your talk. Hanmant? Okay.
Can you hear me?
Yes, you can hear and see you.
So hello everyone. Today's topic for my presentation is drawing a numerical data by using the gunplot software. So here initially when we are before plotting the data, first we need to create the model, and then for the model we need to do the Gaussian calculation. So that one we already did in our lab. So based on the calculation, we need to extract the data from their output file. So here we use the perl command to extract the data for the output file which we generated based on the Gaussian calculation. So here what we did, we extracted data for the alpha orbital as well as for the beta orbital. So once we generated the extracted data, here what we see the different output files for the density of states, for the energies. So to visualize the output files, we use the more command. So here we visualize the density of states alpha orbital file, where we can see the different columns where it represents the energy at the end of the column and in between the intensities of the density of states. So once we generated these output files based on the Perl command, in next stage, we need to plot the data. But before plotting the data, what we did, we for the simplification, we copied that file in the simple forms. So here we copied for the alpha orbitals as well as beta orbitals. And once we copied that file, in the next step, we are going to plot that data using the gunplot. So here in the Photon server, we can directly launch the gunplot software because it is already pre-installed on it. So for that, we use the GNU plot command for that, and once we enter that command, it will automatically launch the gunplot software onto it. So we can see that it is showing we are inside this particular software. So once we inside this software, we can use this command to plot the data for the alpha orbital. So once I entered this command, so first one is for the alpha, second one is for the beta orbital, where we are just plotting the data for the first and second column. And here, based on this command, in upper side, we plotted the data for the alpha orbital, and in downward side, we plotted the data for the beta orbital. As well as for the labeling the axis, we use the set X label orbital energy and set Y label DOS command. We use this command, and we are putting the labels for the graph. So when we want to combine these two data, that time we use this particular command. And once we enter this command into the once we enter this command, we will generate the .ps file for this. So that one I will discuss in next slide. So here, instead of launching the gunplot software, we can just directly use this command to create the .ps file. So here, once we enter this command with using this file, it will create the this .ps file for generating the plot. So here, by using the load command as well as by using this command, we generated that .ps file. So what is this particular file? So here, when we check this file, or by using the more command, once we check this file, here in this file, what we see, it generates the output based on what we are given the name, and it will label the axis what we are shown here, what is shown here, as well as it is combining the data which we already plotted for separate graphs, and based on that it generated the PS file. So that generated PS file, then we plotted we use this particular input file for plotting the data in the PDF format. So for that we use this command PS to PDF command, where we converted that particular file into the PDF format. So the generated PDF file, then we need to transfer on our local computer. So for that we use this SCP command, where we transfer this file on our local computer, and then we will visualize in Adobe Reader. So where we can see the output for the density of state, where it will shows the valence band and conduction band, and these peaks are showing the higher occupation of these orbitals. Thank you. Any question?
Okay, please join me in thanking Hemant. So any questions to the speaker? I really like it. It was very clear. Let's just check if it's just a ready instruction to follow. No questions from my side. Let's check in the audience. More questions, 1. More questions, 2. More questions, 3. Okay, please join me in thanking Hemant once again.
Thank you.
And Hadassah, please start sharing your screen. I hope all attendees have a few minutes more to attend and follow this presentation. Okay, Hadassah, if microphone and camera, are they enabled?
Yes.
Okay, yep, please go ahead.
All right, so my presentation's molecular orbitals, form check cube-gen and isosurfaces, and it's a similar topic to what we've seen. I'll talk a little more about the aspects on if you have a open shell orbital. So molecular orbitals in general, and as people have mentioned, they're positions where an electron of a molecule may be located. And each molecular orbital can have its own energy. There may be more orbitals than electrons, and there can be occupied or unoccupied orbitals, hence the HOMO and LUMO abbreviations. We care about molecular orbitals since they give us information about electronic structure. That can help us predict material color, and they can also help us look at conductivity. And we can also use them to compare orbitals with unpaired electrons, like the alpha beta or the spin up and spin down. So for this presentation, I'm assuming we've already constructed a molecule in Gauss view. An optimization's been complete. We have a .check file, which is in our Gauss view. It's an intermediate result file, and it includes the spatial distribution of electrons, which, as has been shown in other presentations, you can see in a .log file. We're drawing the molecular orbital. First, we can use the form check. This command has the purpose of converting checkpoint files into files that have some format that can be put into visualization software. So you just type in form check and then the name of your file .check. Once you do that, you'll get this output that tells you that the coordinates have been transformed. Once you do that, you can use cube-gen. It generates cubes or files that can be mapped to a .cube file. For this command input, you'd have the name cube-gen, the number of processes, which refers to the processes for a supercomputer working on it. Then you can enter the kind, which would be MO for closed orbital shell, and then it'd be AMO or BMO for the either alpha or spin up or spin down molecular orbital, beta, like beta molecular orbital, and then a number of them. Then you have the .fcheck file, and then you have the new file name or cube. When you do that, you won't see anything new in the command line, but you can go into Gauss view where you can open the file. You just make sure you select .cube files. When you do this, you get your a picture of your molecule. I somehow in the process of the fcheck file, some of my hydrogens got disconnected from other molecules of this titanium oxide. But for the purposes, you could still generate surface contours. When you do that, you go to the results section. There's surfaces and contours. You'll get a dialog box that opens up here. You can go to surface actions and select new surface. And when you do that, you get this representation of molecular orbitals. It can be hard to shrink or adjust the balloon sizes, which are isosurfaces, which have been discussed in earlier presentations. You can go to the ISO values box and select a new value. And then you can go to surface actions. You can now see like there's the 0.2 or the 0.8 from before, 0.08 from before. And when you do that, you have the option to hide or remove a surface. And once you do that, you can see these values, the molecular orbitals a little easier. And if you have multiple, in the case of an open shell, alpha molecular orbitals and beta molecular orbitals, you can cross compare them, which we did in our lab last week. And yeah, so that's alpha and beta molecular orbitals showing. Are there any questions?
Okay, please join me in thanking Hadassah. So presentation is open for discussion. Did you notice differences of the shapes between alpha and beta orbitals? Like, can you comment on how you visually see the similarities or differences? And like, do you expect it to be general trend or just specific of individual system? Just share your observations.
I guess from what I could gather from mine, which I am aware that my molecule is probably not the best to visualize it in front of seen in class. The clusters, the red and the green ones can vary, or some of them can match up from AMO to BMO. For example, this AMO and BMO are similar since they match up to one another. Some of them are because it's the same level of orbital. Others can appear similar, but I guess depending on the energy level, depends on where the balloons get clustered.
Okay, yeah, thank you. Are there more questions to Hadassah from the online audience? Question 1, questions 2, questions 3. Please join me thanking Hadassah and all presenters of today's session. So I believe the recordings went well and it can be shared with all attendees as a reference. All presenters of yesterday and today get a credit so that you are successfully going towards highest grade in the course. So it will be noticed on like campus connections. And tomorrow we will start new software. There will be food for thought. Then I believe we will have a spring break, right? And after spring break, we again will make a marathon to, it will be like maybe 2-3 weeks to cover density functional theory and VASP software. And then we'll have another presentations. And after they're done, on the labs, we will do projects, and on the lectures, we will do TDDFT, and then semester will be done. Okay, many thanks for your active participation. I hope everyone enjoys and finds it useful as a steps towards your research and projects, and looking forward to see you tomorrow in the lab. Okay.
Thank you.
Meeting is done. Everyone is welcome to disconnect. I'll stay here if there will be any questions to discuss.